Welcome all of you. Today we will be discussing the last module of the subject PSA, that is Power System Stability. Like the fifth module, this module is also very easy where you can score 20 marks for the university exam. So by seriously considering the last two modules, it is possible for you to get a pass mark for this particular subject. Now this is mainly theory oriented, yet we will be discussing some tutorials, but most of the marks will be asked for the theory areas. Okay, let's proceed with this module, Power System Stability. Now this is your syllabus and the reference text that we are using here is Kothari, Modern Power System Analysis by Kothari, and these areas will be covered in this lecture. Yes. Now let's give an introduction to the area. That is, here it is discussing power system stability. That means so far in the first module we have discussed the representation of power system, then we have discussed different faults occurring in a power system, then how we calculate the different parameters using load flow, then how actually power is being generated, what are the different controls associated with it, then how this power is being distributed economically, that is the economic load dispatch. And now we will be discussing the entire stability of the system that we were discussing in the previous 5 modules. So in this case, let me brush up with you the basic concept of power generation. So how this hydropower is being generated, or rather how this power is being generated, whether hydro, whether thermal, or whatever it may be, ultimately power is generated with the help of a generator, right? Or you can say an alternator. Okay, so this is the stator and rotor of an alternator. Now, in practical case, the rotor is connected to a turbine. Okay, this also we know, isn't it? Turbine. That's turbine. When the turbine rotates, the rotor of your machine also rotates. Now, how the turbine rotates? The turbine is given an input, and that input is nothing but steam, isn't it? Steam input. If it is a steam turbine, it is like that. So if I am considering a steam turbine, I can say that when a steam input is given to that particular turbine, turbine rotates at a particular speed. That turbine is connected to the rotor of our generator. So if turbine is rotating at a particular speed, your rotor also will be rotating at that particular speed, like that, isn't it? So this is a basic concept. But the generator that we are using is what generator? That is synchronous generator, or SG, or otherwise we call it by the name alternator. Clear? So what is the peculiarity of an alternator? What is the speed of an alternator? Yes, the speed of an alternator is equal to what? Ns. What is Ns? Ns is the synchronous speed. Okay, so what do you mean by synchronous speed? Synchronous speed is actually the speed of the rotating or the revolving magnetic field. That is a synchronous speed. Okay, so that concept is not required in the stability. We just require is your rotor will be rotating at a speed is equal to synchronous speed. Okay, so which is actually the speed of your stator. Okay, so stator and rotor, I can indirectly say that your stator and the rotor will be rotating at a speed is equal to synchronous speed. I cannot say stator, the magnetic field of the stator, and your rotor will be rotating at a speed is equal to synchronous speed. Or I can say there is no speed difference between your stator and your rotor. Both are rotating at the same speed. So this is the stable case, or we can say that your machine is rotating at a speed is equal to synchronous speed. So if this is the case, you can say that your power system is completely stable. Okay, so that means here the stability of a power system is being discussed by considering the speed of your machine. Okay, if your machine is rotating at a speed is equal to synchronous speed, you can say that your system is stable. Am I clear? So indirectly, how can you say that your system is unstable or unstable? That means whenever your rotor's speed is less than or greater than the synchronous speed, Or you can say that whenever your rotor is not rotating at a speed is equal to synchronous speed, you can say that it is falling out of step or it is losing synchronism. Am I clear? So whenever your rotor speed is not is equal to synchronous speed, you can say that it is losing synchronism or it is falling out of step. If that happens, you already know it is a synchronous machine. If its speed is not equal to synchronous speed, the machine cannot work properly. You know it, right? So as long as your machine speed is equal to synchronous speed, you can say that your system is stable. Whenever your machine speed is trying to get out of that synchronous speed, you can say that your machine is falling out of step or your machine is moving to instability condition. So a power system stability here mainly associated with the speed of your rotor. Okay, now from the figure that I have drawn here, which all factors can affect the speed of the rotor? Yes, one factor is the loading condition, isn't it? Loading condition, depending upon the electrical load, okay, the speed can vary. Or indirectly, I can say that whenever there is change in steam input, what will happen? The speed of the turbine varies, right? Then your speed of the rotor also will try to vary. That means your speed of the rotor will move out of synchronism. So these are some factors which affects the stability of power system. Okay, suddenly when a fault occur in the power system, it can affect the speed. Whenever the steam valve is being some damage happen to the steam valve, it can affect the synchronous speed. Okay, like that n number of reasons are there to make the rotor to move out of synchronism. Or indirectly we can say that some factors are there which affects the stability of a power system. So in this module, we will be mainly discussing the stability aspects, the types of stability, how you can analyze stability, or what are some application of the stability criterions. Okay, so these are the things that we'll be discussing in this module. So, so keeping all these concepts in mind, I can define the stability as the stability of an interconnected power system is its ability to return to normal or stable operation after having been subjected to some form of disturbance. Now, what is the stable condition? Stable condition means synchronous condition or machine rotating at a speed is equal to synchronous speed is a stable condition. So how can you say that when your machine is stable? Okay, when a machine is stable means it is rotating at a speed is equal to synchronous speed. Okay, what do you mean by stability of a system? You can say that a particular system is stable if some happens, your machine will try to get out of synchronism, and if the same machine can make the system back to its synchronous speed, or the same system if it is capable of returning the system to the normal operating condition or the stable operating condition, you can say that your system is stable. Okay, it is actually the ability of the system. Okay, if a particular generator or a power system with all the accessories are there, it is capable to make your machine back to synchronism even when some disturbance occur to that system. You can call that system as to be stable system. Now, similarly, what do you mean by instability? Instability means your system cannot bring your machine back to synchronous speed. Once a disturbance occurs, when it loses its synchronism, your system cannot bring back the machine back to synchronous speed. Then you can say that that particular system is highly unstable. Okay, so from these aspects, what I'm trying to convey is that the stability has something to associate with the synchronous speed of a machine. As long as your machine is rotating at speed is equal to synchronous speed, your system is stable. Unless or in the other case, you can say that your system is moving out of stability. Hope this much is clear to you. Now we will see what are the types of stability. So this is again a short answer question. It can be asked in the university. Classify stability, different types of stability. Even it has been asked as an essay question. So if it is asked an essay question, you have to quote some examples from your knowledge gained in all the 5 modules. Okay. So power system stability can be mainly classified into 3. That is steady state stability, dynamic stability, and transient. Steady state, dynamic, and transient. Now we will see what is this steady state stability. Okay. So in the case of steady state stability, so steady state stability means here if consider a system. This is a synchronous machine. Okay, a stator and rotor. It is normally stable. That means your rotor is rotating at a speed is equal to synchronous speed. Okay, normal operating condition or the steady state or the stable operating condition. Okay, now by some means or some small, very small disturbance occurred to your rotor. What happens? The rotor move out of synchronism, or rather its speed variation occur to your rotor. But due to the inbuilt what do you call the damping systems of the machine, the system again returned back to its synchronous speed and again became stable. Then some more disturbance has been occurred to your system. What happens? Again your system will move out of that particular speed and it will return back if the disturbance is very small. Again gradually if I am increasing the disturbance step by step, there is a limit. Okay, beyond which if I am increasing that particular disturbance, your machine will move out of synchronism and will not return back to its initial state. Am I clear? So this type of stability or instability is called by the name steady state stability. That means gradually increasing a disturbance step by step. So that means if you are increasing the disturbance in a very small step, the machine can withstand that disturbance. But if it exceeds a particular limit, the machine will move out of synchronism and it will not return back to its initial state, or it will completely become unstable. Okay, that type of stability is called steady state stability. That means here we will be applying is basically concerned with the determination of the upper limit of machine loading before losing synchronism, provided the loading is increased gradually. So if I have here I have mentioned about some disturbance. The disturbance is nothing but the loading to a particular machine. If you're increasing the load to a particular machine, obviously the machine will have a tendency to move out of synchronism. If you're increasing that load gradually, for some disturbance it will get adapted, but later on if you are further on increasing the loading for in a beyond a particular limit, that machine will move out of synchronism. That is actually the steady state stability upper limit. There is a particular limit beyond which if you are increasing the loading, the machine will fall out of synchronism. That limit is called steady state stability limit. So this type of stability is called steady state stability, where even when the load is increased gradually, if a small disturbance is increased gradually, if your system is capable of bringing back to its initial state or bringing back to synchronism, you can say that your system is steady state stable. And there is a limit beyond which if you are increasing your disturbance, the machine will lose its synchronism and it become unstable. That limit or that upper limit is called steady state stability limit. Okay, so the key point that you have to note here it is the gradual increase of load is associated with steady state stability, not sudden increase, gradual increase of the disturbance. If a system is capable of withstanding that gradual increase in load, your system is steady state stable. Now the next is dynamic stability. Okay, so dynamic stability, some examples for the disturbances are turbine speed, loadings, etc. This speed we have discussed how this speed affects the speed of the rotor. Okay, so these are actually very small type disturbance, very small disturbance. It will not make the machine to lose a synchronism. Okay, but a very small disturbance if occur to a particular system, what will happen? The system is capable of bringing back your machine to synchronous speed, because it is not a very large disturbance, very small disturbance. The machine will not lose move out of synchronism, but still there will be small variation in the speed, still it will not move out of synchronism. Normally it will not create any instability, but it will create some oscillations in the rotor. And if these oscillations are not damped properly, these oscillations can increase further and can make your system to move out of synchronous speed. Okay, so that type of instability is called dynamic instability. What was steady state instability? Steady state stability means if your system is capable of withstanding gradual increase in load, then your system is steady state stable. Okay, dynamic stability means there is no gradual increase in load. If a small disturbance occur to your system, normally your system will not move out of synchronism, but it can create that small disturbance can create oscillations in the system. If these oscillations are not damped properly, what can happen? These oscillations can create very large natural oscillations, and these oscillations can make the system move out of synchronism. That is actually dynamic instability. So if the system is said to be dynamically stable if the oscillation do not acquire more than certain amplitude and die out quickly. So the main thing that you have to differentiate between steady state stability and dynamic stability is that in steady state stability, small disturbance is being increased gradually and we are trying to reach a limit. That is steady state stability. Dynamic stability means we are not increasing the disturbance gradually, but if a small disturbance like change in speed of the steam turbine or change in loading, some small disturbance occur to the system, it will not lose synchronism normally, but it will create some oscillations. If these oscillations are damped in a proper way, your system will be stable. If the oscillations are not damped, these oscillations can cause your system to move out of synchronism. That type of a system is called dynamically stable or unstable system. So your system may be dynamically stable if the oscillations die out quickly. Okay, in an unstable system the oscillation amplitude will be very large, and that means or they are under damped. You know what is damping, right? If your damping of the machine is good, then oscillations will die out quickly. If the damping is very poor, that means if your machine is under damped, the oscillations will not die out quickly. It can cause instability to that system. That type of instability or that type of stability is called dynamically stable or dynamically unstable system. And how these oscillations can be minimized? This can be minimized with the help of power system stabilizers. Okay, so dynamic system study is carried out for at least 5 to 10 seconds. It is not happening in a fraction of a second, because a very small disturbance occur to a system. For oscillations to form, it will take some second, right? So that oscillations, if properly damped, that means your oscillations will die out quickly, then your system is dynamically stable. If your system is under damped, the oscillations will not die out quickly, instead the oscillations will create more amplitude and your system will be unstable or dynamically unstable. So hope the difference between steady state and dynamic stability is clear to you. Steady state means gradual increase of disturbance, but here disturbance is small but it is gradually increasing. Okay, dynamically stable means there is no gradual increase or decrease. A very small distance happens once, it will create oscillations, and if these oscillations are not properly damped, it will make your system unstable. That type of stability is dynamic stability. Now next, and the most important stability that many of our power systems are concerned is a transient stability. As the name indicate, what is transient stability? Transient means sudden for a short duration, isn't it? That means very large disturbance happening within a very short duration. That is called transient stability. Okay, and it is very fast, it is very fast phenomenon, usually occurring within 1 second of a generate. 1 second. Okay, so when a large disturbance may occurring in a system, what happens? There is a very high chance for your machine to go out of synchronism. Again, if your system is capable of withstanding that large disturbance, you can say that your system is transiently stable. But if your system cannot withstand and your machine has moved out of synchronism, you can say that your system is transiently unstable. Okay, so what can be the examples? Fault occurring in a system is an example for transient stability. Whereas what could be the example for dynamic stability? Dynamic stability means small disturbance, right? That is change in speed of the turbine, change in loading, etc. Okay, so very fast or very sudden disturbance and large disturbance is called actually fault. And if that happened to a particular system and your system is capable of withstanding that, you can say that your system is transiently stable. Okay, so that was a classification of power system stability. Stability can be classified as steady state stability, dynamic stability, and transient stability. Steady state stability means very small disturbance increasing gradually. Dynamic stability means very small disturbance which creates oscillations. Transient stability means very large disturbance for a short duration of time. Okay, now we will move on to the mechanics of angular motion, or which are the factors that we need to be thorough before proceeding to different aspects of the power system stability. So you can say that the angular motion, or angular motion means it's nothing but it is associated with synchronous machine. Okay, now these are some assumptions. Let J represent moment of inertia of a rotor. Here we are dealing with the rotor of a synchronous machine. Here J represents the moment of inertia of the rotor. Now omega represent what? Angular velocity, right? Omega sm means angular velocity, that is synchronous speed itself. It is angular velocity in radians per second. Sm means mechanical degree, mechanical radians per second. Okay, so we know that kinetic energy of the rotor. What is the kinetic energy of a linear motion? Kinetic energy is equal to half mv square. But this is rotating, so it can be half. Instead of m, I can write moment of inertia. Instead of v, I can write the angular velocity omega sm square. Okay, that much joule, or that much into 10 raised to minus 6 megajoule. Okay, so this much is clear to you. Now if again in this case, if omega s represent angular velocity in electrical radian per second, here we have represented as omega sem, which represent angular velocity in mechanical radian per second. We are converting that to electrical radians per second, that is mechanical to electrical. Its representation is omega s, and where p represents number of poles of a machine. And we know that electrical is equal to p by 2 into mechanical, or I can say that the velocity of the rotor in electrical radian per second is equal to p by 2 into velocity in mechanical radians per second. Now therefore I can write kinetic energy is equal to, into this equation I can write as half J, instead of omega sm, that is instead of omega sm, I can write it as 2 by p omega s. So 2 by p the whole square into omega s square into 10 raised to minus 6 megajoule. So that's it. Or I am rearranging it as half J 2 by p the whole square into omega s into 10 raised to minus 6 into omega s. Here it was omega s square, right? I have splitted it into two omegas, one here and one here. Okay, and this entire term, that is j into 2 by p the whole square into omega s into 10 raised to minus 6, is called capital M, which is again moment of inertia in megajoules second per electrical radian. Whereas Rj was also moment of inertia, but its unit was kilogram meter square. And here this is our standard moment of inertia, which is in megajoules second per electrical kinetics, and therefore I can write that kinetic energy is equal to half m omega s, where m is the moment of inertia in megajoules second per electrical radian, and omega s is the angular velocity in electrical radian per second. Clear? And another term we need to familiarize here is inertia constant h. Okay, again it has something like moment of inertia itself. We are defining one more term, inertia constant, which is actually kinetic energy, stored kinetic energy in a machine divided by rating of the machine. So usually rating of the machine is represented by G. Kinetic energy here we have calculated it as half m omega s. So I can write the inertia constant h is equal to 1 by 2 m omega s by g, whereas m is the moment of inertia in megajoules seconds, omega s is the angular velocity in electrical radian per second, and g is the machine rating, which is usually in MVA. Okay, so or in other words, I can write from this equation m is equal to 2hg divided by omega s. Okay, and how you can write omega s? You know that omega is equal to 2 pi f. So I can write 2gh by 2 pi f, or gh divided by pi f. Pi means other means 180, isn't it? So this much electrical radian. If I am replacing this pi with 180, it would be in degree. Okay, so or in other words, I can write here left hand side it was m, and if I am taking this g over this side, it would be m by g is equal to h by pi f, or h by 180 f. And what is this m by g? M is the moment of inertia, and in megajoules per electrical, whatever it may be, and g is a rating of the machine or the base of the machine. So whenever you divided actual value by base value, it would become your per unit value. So m is equal to h by pi f, where m is in per unit. So this is the mechanics of the angular motion that we need to be concerned here. M is the moment of inertia in per unit. H is the inertia constant. How will you calculate inertia constant is equal to kinetic energy by machine rating. And 180 F, where F is the frequency, and you can calculate kinetic energy is equal to half em omega s, where omega s is the angular velocity in electrical radians per second. So this is the mechanics of a synchronous machine, or angular motion of a synchronous machine. Now keeping these into concern, we will be now discussing the power angle curve. It is very important. Power angle curve or power angle equation can be asked as a short answer or as a part of your essay question. Now we will discuss the power angle equation or the power angle curve. And what is actually this equation? Equation is relating the electrical power generated in a machine to the angular displacement of the rotor. That is the power angle equation. You know the angle delta, right? What is delta? Delta is the load angle or the torque angle or the rotor angle. Okay, that is a variation or the displacement of your rotor. Okay, normally your rotor was rotating at a speed is equal to synchronous speed, and the variation in your angle of the rotor is denoted by the term delta. And power angle equation is the equation governing the electrical power generated in a synchronous machine with the delta. Is there any relation between electrical power generated and its rotor angle? That is discussed under the heading power angle equation. Now this you might have studied in your synchronous induction machine, that subject or that course. Again we will be discussing it once again. So you know that this is how we are representing a generator. Okay, in the reactance diagram first module itself we have seen that how we are representing a generator. So if this is a generator, this is a voltage source, and this is the effective reactance or transient reactance of the machine. So if this is Eg, this you know that one dash represents a transient condition. Okay, so transient model. So and this is the what do you call the winding, winding of your machine, and this is a terminal voltage or Vt. Okay, and we know that this is a generator, right? And the generator means this much is the voltage available at the generator, whereas this voltage minus this drop, you'll be getting this terminal voltage VT. Now your VT will be your reference. So this is your terminal voltage VT. Excuse me. And if this is your current I, this is your current I, this is your reference. I'm considering a reference, that's all. And this is VT. VT is at an angle alpha from the reference. Okay. Now, since this is the current and here you have J, reactance part is only there, you'll be having the 90-degree part, that is IXD. Okay. And we know that this voltage plus this drop will together give your main voltage. So this will be your resultant voltage. Let this resultant voltage be at an angle delta with reference to your reference. Okay, so this is one transient model that you must have studied in your sim. Now with that we are discussing some terms. So this is a network. Here I am considering one generator. Here I am considering the second generator. Okay, let E1 dash is the voltage of the first generator, and this is at the receiving end. So this is the sending end and this is the receiving end. Okay, this also we know, that is I is equal to Y bus into P bus. Now for the network shown, instead of this I bus, which are the two currents, current I1 and current I2. That is I1 is the current in bus 1, I2 is the current to the bus 2. And here which all are the elements, Y11, Y12, Y21, Y22, and here the voltages are E1 dash and E2 dash. Okay, from this I can write I1 is equal to Y11 into E1 dash plus Y12 into E2 dash. This also we know, right? Complex power is equal to P plus JQ, or P1 plus JQ1, which is equal to V into I conjugate. See, these type of derivation we have studied in Gauss-Seidel method. Okay, or other words I can write that P plus JQ is equal to E1 into I1 conjugate. What was I1? This was I1. So I am substituting that I1 over here. I got it as E1 dash Y11 plus Y12 E2 dash the whole conjugate. If you are expanding that conjugate here, E1 dash into E1 dash conjugate into Y11 conjugate plus Y12 conjugate into E2 dash conjugate. And while I am considering this, I am expanding this, it would be E1 into E1. So E1 square into Y11 conjugate plus E1 into E2 conjugate into Y12 conjugate. Okay. So how it became E1 square? This became E1 square. Why? This became E1 square because E1 dash means E1 angle theta. E1 dash conjugate means E1 angle minus theta. So there will be only magnitude part on multiplying this. Okay, that is how it happened. Now we know it already, right? We will represent voltage as magnitude and angle. Second voltage as magnitude and angle. Then admittance as Y11 is equal to Y11 angle theta 11. Y12 is equal to Y12 magnitude and angle theta 12. So substituting to that equation, this equation I can write as P1 plus JQ1 is equal to E1 square into Y11 angle minus theta 11. Why? Because there is a conjugate here. Plus E1 into E2 into Y12, into which all are the angles associated here, delta 1 minus delta 2 minus delta. Why this minus came? Because there is a conjugate here. Now here we are separating the real and imaginary part. Okay, separating real and imaginary part. What will be the real part? Real part will be the cosine terms, right? So E1 square Y11 cos theta 11 plus E1 E2 Y12 cos delta 1 minus delta 2 minus theta 12. And we have studied that y sin theta is B and y cos theta is nothing but G. Okay, because we have studied that triangle, right? Sorry, we have studied that triangle. Okay, here if it is R, here if it is X, here it was Z. If it is 1 by r, then it would be 1 by x, and it would be 1 by z. And if this is the angle theta, you can say that 1 by z means y. Okay, y cos theta means what? 1 by r, right? And what is 1 by r? Is resistance. 1 by r means conductance. So G is nothing but conductance. So instead of y cos theta, I can write it as G. Similarly here, no. So we have replaced E1 square into G11 plus E1 into E2 into Y12 cos delta 1. Okay. Now we are giving some notations over here. Let this entire thing be represented by PC. Then E1, E2, Y12 will be represented by P max. Delta 1 minus delta 2 be represented by delta. Theta 12 is equal to pi plus 2. Pi by 2 plus gamma. Gamma is yet another value we will discuss. Okay, so if these much assumptions are made, you can write P1 is equal to PC plus P max cos delta minus pi by 2 minus gamma. What is delta minus pi by 2 minus gamma? You will be getting it as sine delta minus gamma. So you can write P1 is equal to PC plus P max sine delta minus gamma. Okay, or P1, what is this actually? P1, what is this P1? It is a power generated by the first generator, right? So you can write that instead of P1, you can write it as PE, where PE represents electrical power generated, which is equal to PC plus P max sine delta minus gamma. What is PC? PC is equal to voltage into conductance. Voltage square into conductance. Voltage square into conductance means actually I square into R. Okay, or it is, what is I square into R? I square into R simply means what? I square into R simply means power loss. So PC represents power loss. P max represents maximum real power that can be transferred. Delta is the load angle. Gamma is yet another angle that we'll be discussing. Okay, this is called the power angle equation. This is very important. P is equal to PC plus P max sine delta minus gamma. Gamma is any value with which this current is being deviated, that we will see when the load, depending upon the load. Okay, so PE is equal to, P means electrical power generated, is equal to the losses, which is a constant part, plus P max, maximum real power that can be transferred, into sine delta minus gamma, where delta is the load angle. Now, usually our what do you call, transmission network is purely, we are assuming it as a purely reactive. If it is purely reactive, we can say that we don't have any much power loss. That is, I square R loss is very low, and your angle will be 90 degree, or theta 12 will be 90 degree, or you can say that your gamma is equal to 0. Okay, so you can see that see your gamma here, you have represent theta 12 is equal to pi by 2 plus gamma. So you can write gamma is equal to theta 12 minus pi by 2. Okay, gamma is equal to theta what do you call, theta 12 minus pi by 2. So when you say that your system is purely inductive, that means your theta is equal to 90 degree, isn't it? Theta is equal to 90 degree, so your gamma will be equal to 0. Gamma will be equal to 0. Therefore, you can say electrical power generated is equal to P max sine delta, where P max, what was P max? P max was E1 into E2 into Y12. Y12 means what? 1 by Y is Z, or that is Y is 1 by Z. What is Z? Z is equal to R plus J X. Okay, So instead of y12, I can write 1 by r plus jx. But we have assumed that this is a purely inductive. So there will not be any r. There will be only x. So I can write P max is equal to E1 E2 into Y12 or E1 into E2 by X12. And this equation is our simplified power angle equation. Very, very, very important. And this power angle equation actually gives a relationship between electrical power generated PE and the angle, load angle delta. Okay, so electrical power generated PE and the load angle delta is given by the equation PE is equal to P max sine delta, where P max is the maximum power that is being generated and delta is a load angle. P max is equal to E1 into E2 divided by X, where E1 is the sending end voltage, E2 is the receiving end voltage, X is the reactance of the transmission line connected between the sending end and the receiving end. Okay, this is the power angle equation, and with reference to this power angle equation, now let's see the power angle curve. This is a power angle curve. This is the electrical power PE, and this is the angle delta. We can say that PE is equal to a constant into sine delta. So PE is a function of sine. So its curve will be like this, isn't it? Sine delta. The what do you call? You can say that this equation will be low when delta is equal to 0, PE is equal to 0. PE will be equal to maximum when delta is equal to 90 degree. When delta is equal to 180 degree, again your electrical power will be equal to 0. So that is this curve. And at pi by 2, you will be getting the maximum power that you have represented as P max, which is equal to E1, E2 divided by X. So this is a case for a generator, or this is a case that we need. But the same thing, if it is a motor, it would be the reverse. That is the maximum power that is being consumed. This is the maximum power that is being generated. Okay. Now just leave this part because we will come to it while we discussing about the swing equation. So in this section, we mainly discussed the power angle equation, that is the equation between equation which shows the relationship between electrical power generated PE and the load angle delta. Okay, so in this lecture video we have mainly discussed what is the concept of stability of a power system, what are the different types of stability: steady state stability, dynamic stability, and transient stability. Then we have seen the angular of the mechanics of the angular motion, that is about how you represent kinetic energy is equal to what is moment of inertia, m is equal to h divided by pi f, or 180 into f, its units. Then the power angle equation, that is PE is equal to P max sine delta. That is a simplified form of the power angle equation, where P max is the maximum power that is being transmitted from one section to another section, that is from the sending end to the receiving end, and P max is equal to E into V by X. What is E? E1 is the sending end voltage, E2 is the receiving end voltage, X12 is the reactance of transmission line between the sending end and the receiving end, and delta is a load angle. Hope this much is clear to you. If you have any doubt in these sections, please feel free to contact me. Thank you.